Hi, I'm Dalton, and for the Lab 5, I'm doing the falling slinky. So here's an introduction and some of the fundamental principles. The overall purpose is to see how the top of the slinky falls in relation to the bottom of the slinky. I'll be using Newton's second law for this, and then the system and surroundings, we'll go into those. The system's going to be the spring or the slinky, and the surroundings is going to be the earth and everything else. And then a quick preview is that the top is going to fall before the bottom starts to fall. So here are some of the basic equations I'll be using for this. We have velocity update, position update, spring force, and the force of drag equation. So here's the video if you want to watch that, and the initial conditions, which you can see set over here. We have our position, velocity, mass, a spring coefficient, and the drag coefficient. All right, and then here's the glow script code. Over on the left, I just set up all of the initial conditions, the time step, position, and all those things. And here in this while loop, we're just calculating the net force and how that changes the ball's velocity and position in each time step. And then finally over here on the right, I'm updating the ball's velocity and the position before it gets plotted. So here is the results graph, where in blue we have the tracker and in red is the glow script data. The reason that the tracker looks not quite as good of a line as the other is due to some errors when I was tracking it in the tracker software, not being able to tell where the slinky was, just due to the frame rate. And as you can see, they're pretty close, which goes to show that the glow script model pretty accurately computed what happened in the real world. Even though these differences are visible, they're pretty minimal, so I would say overall it's a good computational model. Of course, it wasn't perfect though. There are some possible sources of error. One of the main ones is that there was no calibration that was 100% accurate in the tracker. And this was not due to a lack of trying. There was just nothing such as a meter stick that I could use to get an accurate measurement. So to go around that, I guessed the height of the man in the Veritasium video based on internet data, which was approximated to be around 1.75 meters. Another definite source of error could be the drag coefficient. This is not something that I calculated based on real world data, and it's more of an estimate to get the data to work appropriately, so that could be wrong. And then that same kind of thing applies to the K value, which I just also kind of guessed to get a force for the spring that would somewhat accurately make the data do as I needed it to do. So now we'll do a what does it mean question, and that's going to be why did the top of the slinky fall before the bottom fell? This is something that's really not too complicated. It's just because the spring force that exists in the slinky, which is essentially a spring, was the appropriate amounts to balance the gravitational force that existed while the spring or slinky was in a stretch position. So as it fell, of course this did change, but as the compression changed, that force also kept varying, and that was enough to consistently balance gravity throughout the motion. And that's why when we finally got to the bottom and there was no more spring force, the full effect of gravity could be seen, and the spring did start to fall. And then I have one more question, which is what if we change the initial stretch in the spring? The same thing would happen as before with the top falling before the bottom. The only difference is going to be the amount of time that it takes. And obviously if we stretch the spring more, it's going to take more time to fall, and less would be less time to fall. But overall, that sums up how the slinky worked in this situation. So thank you for watching.